Okay, so what I'd like for each of you to do is take a few minutes to write the electron configuration for copper and chromium, get out your periodic table, and I want you to do this shorthand. Pause the video while you do this and then pick back up. Check your answers. I'm going to go ahead and look on the periodic table and see where both copper and chromium are located. So we're going to look at chromium first. We'll do a shorthand. If you notice in the period above him, the noble gas in the period above him is argon. So we're going to put argon in square brackets. And then you're going to pick up here, and this is your fourth energy level. These are your s orbitals. So we'll say 4s2. And then you're going to say 3d1, 2, 3, 4. Now this is based on what we've learned so far. Do the same thing for copper. Okay, here's copper. So same thing, going to period above them and go to the noble gas. Put the noble gas in square brackets. Argon in square brackets. 4s2, and now we're going to go 3d9. Hopefully that's what you got for your electron configurations for copper and chromium. That's based on what we've learned so far, but there's something I haven't told you yet. These happen to be two of the exceptions to the electron configuration. So we just said chromium, you would think, would be argon in brackets, 4s2, 3d4. But one thing I haven't told you yet is that completely filled orbitals and half-filled orbitals are extremely stable. Completely filled orbitals and half-filled orbitals are super, super stable. And we've learned over and over again that the elements just want to be stable. So what do I mean by that? Well, half-filled orbitals would be like this. An s orbital is half full when it has one electron in it. That's just one Y. A p orbital is half full when it has 3 Ys. A d is half full with 5, and an f is half filled with 7. Likewise, if we have completely filled orbitals, what you have here in the second column. So a full orbital for an s is an s2. For a p, it's a p6. For a d, a d10, and a f, a f14. This is extremely stable, and this is something that copper and chromium can both do very easily. Look at what we have here with the s orbital for chromium. It's an s2, so it is completely filled, which is great. But the s orbital will be just as happy if it were s1. The d orbital is one away from being half full. Notice it has 4 electrons in it. If it was a d5, that would be best. So what chromium is able to do is it's able to take one of the s electrons. Let me draw this with your orbital notation. This represents your 4s orbital. And if you look at your electron configuration, that's what we've got going on right now, 4s2. And then the d orbitals, remember, we could draw 5 subshells. And according to this, there's 4 electrons in it right now. So that means up, 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 up. So what happens here is the 4s orbital, since it has the ability to donate one of his, because the electrons belong to him, this electron here kind of comes out spinning, and it lands in here into this empty house, this empty room, and it spins up. Because they can just flip around once they come out of their boxes. That's going to give you 1, 2, 3, 4, 5. So this becomes half filled, which is very stable. And this one becomes half filled because now there's only 1 electron in there, 4s1, which is fine with him too because he's still stable. So the actual electron configuration for chromium is argon in square brackets, 4s1, 3d5. This happens to be the ground state for chromium. This is his most stable state, and this is what you would always want to write for chromium. A similar thing happens with copper. One of the electrons from the 4s gets promoted, and that's why this becomes 4s1, 3d10. The 4s orbital is half filled. The 3d orbital is completely filled. Now, the reason this is able to happen is because since the electrons all belong to the atom itself, if it's able to arrange its electrons in such a way that makes it more stable, it will do that. So what happens here is one of the electrons gets promoted. It's called electron promotion. Remember that. And it happens because full or half-filled orbitals are extremely stable, and they want to be happy. They want to be stable. So the elements are going to do what they need to do to be stable. The next thing I want to look at is some things I want you to be able to interpret from your electron configurations. There's 4 questions I want you to be able to answer based on a given electron configuration like the one you have here. The first thing is I want you to be able to tell me who the element is. So remember, the best way to do that is to add up the superscripts, find out how many electrons you have, and that will equal to the atomic number because these are neutral atoms. So let's add up all of our superscripts. 2 plus 2 is 4, plus 6 is 10, 11, 12, plus 6 is going to give you 18, 19, 20, plus 8 is 28 total electrons. So that means that the element that the electron configuration represents is element 28, which is nickel. Okay, so that's the first question I want you to be able to answer, is who is the element? Now the next thing I want you to be able to answer is I want you to be able to tell me who the highest occupied energy level is, or what the highest occupied energy level is. I will always abbreviate that HOEL for short. Now this represents your valence shell. The valence electrons are located in the highest occupied energy level. Now remember, in your electron configurations, these big coefficients, the 1, the 2, the 3, the 4, the 3, represent your energy level. Well, in this case, the highest one that's occupied by electrons, I'm going to circle it, is the 4. So you would tell me it's the 4th energy level. The valence electrons are located in the highest occupied energy level. So there's 2 valence electrons. That means the rest of the electrons are the core electrons. So if you were to add up the rest of the electrons, the other superscripts, you'd add 8 plus 6 plus 2 plus 6 plus 2 plus 2. That's going to give you a total of 26 core electrons. What you want to recognize here, y'all, is these 2 numbers have to add up to the total 28 that we got up here. Okay? So 2 valence, 26 core. This is how you find the valence electrons for your transition metals and your lanthanides and actinides. Remember, there was no pattern for those. All right, I want you to try this next one. Try this one on your own. Please pause the video while you're doing it and then pick up and check your answers. I'm going to go ahead and complete it. Add up your superscripts to figure out who it is. So we have 10 plus 1 is 11, 12, 13, plus 6 is 19, 20, 21, plus 6 is 27, 28, 29, 30, 31. So we have 31 total electrons. All right, that means that the element represented here is gallium. Highest occupied energy level, circle the 4th here. That's the highest energy level represented. And I circle both of them because, y'all, that is where the valence electrons are. You got to add the total. So you have 2 and 1. 2 plus 1 gives you 3 valence electrons. So you have 3 valence electrons. And finally, the core electrons are all the rest that you have in the core of the atom. So if you add these 2 numbers together, remember they have to add up to the total 31 that we got a while ago. So 29, excuse me, you got to add here, that would be 28, sorry y'all. 28 electrons are in the core. All right, that's it for today.